This is 7-8 geometric sequences. Our learning objective is to write and use recursive formulas for geometric sequences. We're also going to do explicit formulas. So let's put that on there. Recursive and explicit formulas for geometric sequences. So definitely write that down. Let's get the highlighter. So our essential understanding is in a geometric sequence, the ratio of any terms to its preceding term is a constant value. Boy, that's pretty mathy. So let's figure out how to interpret that in real languages. So ratio is like a multiplier. So the ratio, when you multiply by the same item, the ratio of any term to its preceding term is a constant value. So if I have 2, 4, 8, 16, 32, then the ratio between 2 and 4, so 4 over 2, and then the ratio between 4 and 8, 8 over 2, and the ratio between 8 and 16, and the ratio between 16 and 32, all those ratios are equal to a common ratio. And I consider that common ratio a multiplier. Because each time, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. It's what I multiply by every time. We are calling it the common ratio here. Okay, so it's going to get pretty mathy up in here. A geometric sequence with a starting value of A and a common ratio of R is a sequence of the form, start with A, and then you multiply it by R. A times R, and then A times R squared, and then A times R to the third, etc. forever. Alright, so I'm going to highlight recursive formula because this is the hardest item to understand. And I'm going to put it together for you. So a recursive formula says, how do I get from my current term to the next one? So all you care about is the term you're on and the one right next to it. You don't care about anything else, just that process. So they have this little wonky subscript formula where you have to list your first item and then how you go from the first to how you go from term to term. So in this case, in our 2, 4, 8, 16, 32, what is our first term? It's listed. 2. Okay, I'm going to do some work. So I'm going to put the work over here, and then I'll put the answer over here. N kind of stands for next. So the next term, so A, if I already have 1, so the next term would be this second term in the sequence. So that little baby 2 means term 2. So little baby 2 is term 2. So this is A1, A2. 8 would be A3. So to get to A2, I'm going to take A, n means the current term, 2 minus 1. See how this is in baby? I'm not multiplying by 2 minus 1. The only thing that's getting some math is just the 2 minus 1 itself. Times r, and here we found our multiplier, our common ratio was 2. Okay, so what this says is my second term I'm going to get by taking, what's 2 minus 1? My first term, so a to the 1, and multiplying by 2. Because that's our. So my recursive formula is going to be a to the n minus 1, and all that minus 1 says is go back to the previous term. It says go back 1 times 2. So what we did right here with a1 equals 2 and a to the n equals a to the n minus 1 times 2 is we wrote a recursive formula. So that's if I have 4, I know how to get to my third term. I just multiply 2 and I get 8. If I'm at 8, I know how to get to my next term. I just take 8 and multiply by 2. So each time we're multiplying by 2. You have to identify what your starting value is, because I could technically start this at 16 and it would still be the same process. I'd still be multiplying by 2 to go from term to term. Now, what if I ask you something crazy like, what's the 100th term in this sequence? I don't want to have to multiply 2 by 2 100 times. So, so what we can do is we can create an explicit formula. And that is when all I have to do is plug in which term I want. So if I want the 100th term, I just plug in 100. And I get out what that's equal to. So if I were to find an explicit formula for my sequence, I would first have to know what my first term is. That's this guy right here. A to the 1, and we know that it is the number 2. And then I'm going to multiply that by, so I'm right here, our common ratio, which was 2, multiplied by 2 every time, and then I've got n minus 1 up here as an exponent. This is the explicit formula. I don't do anything else with this when I'm just writing the explicit formula. But what I can do is I can say, what is this when n equals, we'll go 20. We'll make it crazy. So then a with a little 20, that means this is the 20th term, is 2 times 2 to the 20 minus 1, which is 2 times 2 to the 19. And if I want to calculate that and get an actual number out, my 20th term is going to be 2 to the 19 times 2. 1,048,576. There we go. Almost lost that too. All right, so you're going to be in your practice problems. You're going to be identifying geometric sequences like they did in this example problem number 1. And for A, by looking at it, you can say, oh, they're multiplying by 10 every time. And if you don't know how, if you can't just look at it and see, like, if it's some weird decimal or a crazy fraction, remember to find the multiplier, you just take the one before divided by the one next to it divided by the one before. B, there's no common ratio, so it's not geometric. C, the common ratio is -1, so it is geometric. And that's something to look for when you see your plus and minus alternating, that your common ratio is probably negative. Because a negative times a negative is positive, and they take that positive and multiply it by a negative, and it becomes negative. Multiply that by a negative, it becomes positive. So here it'll alternate. All right, so let's do a couple of these guys. Let's do A and C. So A is 3, 6, 12, 24, 48. Just by looking at it, can you guys find a common ratio? Is there something that I multiply by each time to get the next one? Yeah, which that is it not. The sequence is not geometric. Is it arithmetic? So here I am actually multiplying by 2 each time. So our common ratio is 2, so it's got to be geometric. C, 1/3, 1/9, 1/27, 1/81. Is this a common ratio? Do I multiply by the same thing each time? Can I give you a hint? What if I were to multiply by 1/3? What is 1/3 times 1/3? Yeah, 1/9. What if I were to multiply that by 1/3? Yeah, so this is geometric. And then just for funs, 3, 6, 9, 12, 15. Is it geometric? Am I multiplying by the same amount every time? It's not. And it's actually arithmetic because I'm adding 3. What about D? We don't have the same adding each time. We can see the pattern. Just because there's a pattern doesn't mean it falls into geometric or arithmetic. This is neither. Because it doesn't have the same amount each time. All right, so we're going to write recursive and explicit formulas for these two. You don't have to rewrite this. I just pulled it over so it's on our same page, so we can have it as a reference. So we are going to do recursive first and explicit second. All right, so recursive, we need the first term, which in this case is 2, and then we need a pattern to get from term to term, so we've got a to the n minus 1, and what is our common ratio here? Oh, we already did this one. This is sweet. What are we multiplying by each time? 2. Done. Recursive is done. Yeah. And I guess just for fun's sake. And yeah. All right, so explicit. We're going to roll out this formula. Our first term was 2. Our ratio is 2, and n minus 1 goes in the exponent. Done. Done. I'm out. All right, now let's do it for something that we're not familiar with. Our first term in B is 40. And to get from term to term, we're going to take the previous term and multiply it by something. So let's see. To get from 40 to 20, what can I multiply by? To go 40 to 20. And we want to be thinking, obviously it's not 2. So what's kind of the opposite of multiplying by 2? We can divide by 2 or multiply by 0.5? 1/2? Okay, so our common ratio is 0.5. All right, so now let's take that information and put together a nice little explicit formula. So our term, any of them, is going to be our first term, which is 40, times our ratio, which is 0.5, to the n minus 1. We're done. That's it. Wow.